Hey everyone, welcome to our channel, Audio Develop. My name is Joel. I'm going to be your instructor for the day. Get your pen, your notebooks ready. We are going to start. So if you've ever wondered how music production software, audio applications, and even gaming headsets process sound in real time, this is the right place for you. So in this video, we are going to build our very first real-time audio application using C++ and something we call PortAudio. And don't worry, if you've never done audio programming before, I'm going to walk you through every single line of code, explaining what's happening and why it matters. And this is not going to be a basic C++ class. No, we're not going to do the basic C++ programming. So by the end of this video, you'll understand the fundamentals of digital signal processing, how real-time audio actually works, and you'll have a working application that processes audio in real time. So stick around and get ready. So before we jump into writing code, we're going to explain what digital signal processing is. Now, I want you to imagine sound as a wave. When you speak into a microphone like what I'm doing right now, that sound is an analog signal. So it's actually continuous, like water flowing from a tap or flowing in a river. And now when it comes to computers, they actually work with numbers. So what happens is we need to convert that continuous analog wave into a bunch of individual numbers that a computer can understand. And in that process, that is what we call digitization. So here's how it works. Thousands of times per second, we measure the height of the sound wave and record it as a number. So this measurement process is what we call sampling. And the number of times we sample per second is what we call sample rate. And it's normally measured in hertz, or you can say Hz. So in our projects, we are using a sample rate of 48,000 hertz. Which means we are taking 48,000 measurements of the audio signal every single second. That's 48,000 snapshots of the sound wave. And okay, you're going to ask, okay, Joel, why 48,000? Why not maybe 72,000? Why not 100,000? Well, there's a principle in audio that is normally called the Nyquist theorem. It normally states that to accurately represent a sound frequency, you need to sample at least twice as fast as that frequency. And because the human ears can hear up to 20,000 hertz, we need to sample rate we need a sample rate of at least 40,000 hertz. So 48,000 hertz is normally a standard used in professional audio production. For anyone who has been working with the digital audio workstations, will understand what I'm talking about. Now, digital signal processing is all about taking these numbers, these digital samples, and manipulating them in a various way. Like you may decide to amplify them or filter them, add effects to them, or sometimes mix them with other signals, or you can do any kind of creative things you want. So that's what we call DSP. And that is what's really cool is that it happens in real time. So like for example, when I play piano, and somebody's singing, so and maybe the sound engineer decides to add an auto tune. So you will your ears will actually perceive the auto tune immediately, like it happens in real time, without even, without any lag. So that's the fun part of digital signal processing. So as the audio is normally coming in from the microphone, we are normally processing it and sending it back to the speakers almost instantaneously. And that's what we call, real-time processing, if you've heard of real-time processing. So I had said we're going to do with something we call PortAudio. Now, what is PortAudio? PortAudio is a C library that actually gives us a simple, unified way to do real-time audio inputs and outputs across different operating systems. So this is why it normally matters, by the way. If you've worked with hardware before, you know the different operating systems like the Mac OS, the Linux. They have different ways of talking to audio hardware. So, for example, Windows use something we call the Wasapi, and for Mac OS, I am actually on Mac OS. We use what you call the callback, and Linux normally uses the ALSA, or sometimes there's this other library. What is it called? I think it's PulseAudio. Yeah, I think it's PulseAudio. And sometimes it's normally a nightmare if you have to support all those, libraries by yourself. So PortAudio solves this problem. It provides a single API, that's application programming interface, that works the same way on Windows, macOS, Linux, and even some embedded systems. So you write your own code once using PortAudio and it just works everywhere. That's the power of abstraction. Now, in our project, we are going to use PortAudio to initialize the audio system, open a stream to your default audio device, set up a callback function that actually processes audio in real time, and manage all the complex details of audio input-output for us. So I want you to think of it like PortAudio is actually handling all the boring stuff in the background, and we got to focus on the fun part of processing the audio. I believe you've understood the theorem and everything up to this point. So before we start writing any code, we've talked about PortAudio and DSP in general and what it does. So we're going to install PortAudio. So I'm just going to open terminal, a new terminal. So if you're on because I'm on Mac, we can, and different viewers have different operating system. I am on Mac, and I'll explain for different how to install on different operating systems. Okay, so we can install it in different ways, but for example, now on macOS you can install it via the package manager, and use the homebrew, for example. Use the homebrew. And for Windows, I think they use the VCPKG, because I remember the last time I was using, gosh, it's been a while since I used my Windows laptop. I think you use the VCPKG, and try to run it from there. So it's not going to be hard installing it. You'll just find the documentation on Google, even on GitHub, on how to install for different operating systems. Another option is you can decide to actually pull and build the PortAudio from the source. If you prefer building from the source, or you don't have a package manager, you can pull the PortAudio repository, build it, and install it. So this is actually normally it's now actually normally interesting if you want to understand where headers and libraries actually live. But it all drops down to somebody's individual interest. So for me, because already I've installed, or if you're on Mac, I'm just going to give you simple. So we can just use brew. Normally use brew. Install PortAudio, and pkg config cmake, and because definite I already have Homebrew installed and everything set up, so definitely it's just going to run. And if you're using Homebrew, you'll have to actually set up its path by using the echo path. You have to set the path. You export the path to where Homebrew is. So that is if you're on the Apple Silicon machine. So already, because I have everything satisfied, I'm not going to try and run again, because I don't want to break anything currently. So if you have everything set up, you have PortAudio set up, so we are going to start. So start by you create the main.cpp file. This is something basic. Hashtag include, and we're going to import the PortAudio header file. I'll explain everything shortly. And hashtag include the input output stream, and going to do const then we do an integer of sample rate. Remember, sample rate, we said it's 48,000, so sample rate equals to 48,000, and tab, and constant the frames per buffer 256, so not 512. Yeah, so what's happening here? So maybe you are new and you're like, Joel, what are you doing? So the include PortAudio.h, this is actually a preprocessor directive. It tells the C++ compiler that, hey, I need to use the PortAudio library in this file. Go find the header file called PortAudio.h and include it here. So the header file actually contains all the function declarations and type definitions we need to use in the function definition that we need to use from PortAudio. So just think of this as a cookbook, like something like a table of contents. So it tells you what recipes are available, what ingredients they need, and what they produce. So like when we include it, we are saying, I want to use these functions. Now we also have the include input output stream. So this is not something new to any C++ developer. So this is just a C++ standard input output library. It gives us the stdc out for printing out in the console, and the stdc in for reading from the console. So we also normally use these to print error messages and instructions to the user. So this is just something simple and something basic. Right. So we get to here. So somebody's like, Joel, what is this? What is all this? So this is actually a constant variable declaration. The keyword, like you see, the keyword const expr, this actually means this is a compile time constant. And this constant is setting the sample rate to 48,000, as we had earlier said. So what does this mean in practice? We are actually telling PortAudio, give us 48,000 samples per second from the audio device. So this is normally this, like I said before, this is normally the standard professional audio sample rate. And I want you to remember that the Nyquist theorem I mentioned earlier, 48,000 means we can accurately represent frequencies up to 24,000 hertz, which covers basically the entire range of human hearing. So which tops up to around 20,000. Okay. All right. So a frame is actually just a fancy word for one sample. So frames per buffer is normally the number of samples we process at a time. So here's why it matters. We don't process every single sample. Like we don't do okay, how can I put this? We don't normally process every single sample one at a time. Because normally it will be so slow, like definitely so. So PortAudio gives us like a chunks of samples. In this case, for example, here we are doing 256 at a time. So we are like processing all the 256 samples together. I hope you've understood like that. So initially, from IntelliSense, it was saying 512. But you're going to ask me, okay, Joel, why did we use 256? So 256 is normally a balance between two competing needs. Number one, lower latency. Smaller buffers means shorter delays between the input and the output, which sometimes feels more responsive if your buffer is normally huge. And you'll notice a noticeable kind of a delay. And number two, there's that more processing power, because larger buffers gives your CPU more time to do processing before the next chunk arrive. So if normally your buffer is too small, the CPU can't keep up. So 256 is normally that sweet spot for most real-time audio application. It gives us about, I think it is 5 or I think 10 milliseconds. I think it's 5 of latency at 48,000 hertz. And that's normally fast enough. Like it feels real time to the human ears. Like, you know, it's going to be amazing. Yeah, so I think you've understood to that point, and we are going to continue. So we're going to, I hope you're following along. So we're going to do a static int. Oh, sorry. Okay, lowercase. Static int. Static int. We're going to do an audio callback. I love Visual Studio because, you know, because of the IntelliSense audio callback, and we're going to do a constant void. There is a pointer and the input buffer. Okay. You know, it's giving us everything that we need, but we're just typing for, you know, to actually help us understand. Okay, it was the output buffer, and I'm going to do, okay, I'm going to drop down. So do the unsigned long. Unsigned long frames per buffer. Okay, frames per buffer. We're going to go down. Okay. There's a typo error above, so we're just going to do something here. Yeah, perfect. So constant. Yeah, I'm going to do constant of PortAudio stream PS stream callback time in 4 tab, and we are not going to pass time in 4 right now, so we're going to do the PortAudio stream flags. Yeah. Okay, stream flag audio callbacks stream flags. Yeah, I'm going to do callback. Yeah, we're going to do a flag, definitely. Okay, fingers crossed it will compile, because we're doing this real time. Okay, so we need to set up something here. We need to set up a comma. Yeah. Okay. And let's just return a void for now. Okay. Okay, let me just check if I'm actually. Okay, so we need to get that thing down first. Okay, so okay, remove this. I don't want that. I want this right now. Okay. All right. So okay, so then I think what I should do, I should write everything. So saying the user data. Yeah, sure. Okay, now I get it. All right. So I'm going to open up. So we're going to do. It's giving us the const float. Yeah. And static input buffer. Yeah, we're just going to tab that. See what we don't need here for now. Okay. So I don't need this. I'm going to change this for now because yeah. So what I'll do, I'll just do an if. That equals to in. So just going to open it. Going to say the std, fill out. Okay, so we're going to return, going to return that. Then I think we're also going to do a for loop. Sign along, from space. Yeah. Okay, I think okay up to now. So I'm going to explain. So this is the part where this is actually the heart of, let me put it this way here. So this is actually the heart of our real-time audio application. So this is now the audio callback function. So I'll just explain what a callback is. So a callback is a function that gives you that you give to PortAudio and say, hey, whenever you have new audio samples to process, call this function. So you're not the one calling the function directly, like PortAudio is calling it for you, like over and over again, 1,000 times per second. So in this function, so we are doing a static. So what does static mean? So this keyword actually means the function has internal linkage. So it's not accessible from outside this file. So this is normally good practice. Like it's just good practice. Like it's like saying this function is private to this file. I hope you understand the private and the public. Then there's an integer. So this is just it's just the return type. Our callback function returns like an integer. So in PortAudio, this integer tells PortAudio that like what to do next. Like what to do next. Like we can return PA continue, which is equals to 0. Like equals to 0 means like keep the audio stream running. PA complete, which is normally equals to 1, like stop the stream. Or PA abort, which equals to 2, or stop immediately. Don't worry about that, we are going to implement them ahead. So for now we are returning PA continue because we want the stream to keep going. And the audio callback is actually just the function name. I hope you understand what a function is and function names and all that. Okay, so the next part, these are what we call parameters. And the const, void, like input buffer, this is actually the audio data that is coming in from the microphone, like right now, or from the line input. It's a void because it could be different data types, like depending on how you configure the stream. So for example, in our case, okay, yeah, he did input buffer, yeah. So for example, in our case, like right now, it's actually a float. Like it's actually a float data because it's actually a float data, right? So it's actually a float data, but PortAudio currently doesn't know that yet. So we can say it's just generic. And for the output buffer, this is where we put the audio data that will be sent to our speakers again. So it's a generic void pointer, hope you understand. If you don't understand, you can just write down at the comments and write say, hey Joel, please repeat this concept for me to understand. I will just do a video. So we have the unsigned long, the frames per buffer. This is actually how many samples we are processing in this callback. Remember, we actually set this to 256 in our constants. So this will be actually 256. And then we have the constant PA stream callback time info. This is timing information about the stream, when the input was sampled, when the output should be played, all that. So we are not using this in our simple example. We are just going to ignore it for now. and we have the the stream callback flags. These are flags that gives us information about the stream status, and for example, like are we late? Is there a buffer underrun? Like we are not using this either for now, and yeah, so we have that. This is just a user user custom data that you want to pass to the callback. So we are not using it also. You just have the generic. Yeah. All right. So in here, this is what you call a function body. And we're just going to explain what this function body does. So we have the float and typecasting. So remember I said like we have like the input buffer is a pointer, so we need to tell the compiler like this is actually a pointer to float data. So this is what I am doing, and the static casts, all these they actually do that, and they actually convert the generic void pointer into these constant floats. So normally a constant pointer to a float, it's like doing a constant pointer to float data. And you're going to ask me, okay, why are we using constant? Because we are not going to modify the input, we are just reading it. That's why we're using constant. Similarly, for the output buffer, becomes a float pointer, because it's actually a pointer to floating to a float data that we can write to. After this, we have this. It's actually this is actually pointing to our 256 input samples, and it's pointing to our 256 input samples, and our out is actually pointing to where we'll write our 256 sample output samples, and it's actually pointing to where we'll do our exactly. So what's happening here, what's happening here, I am actually doing something we call safety checks. So if you've used C++ before, we're doing a safety check. So for example, in this line I am actually doing a line check if the input buffer is actually null. In other words, is there input coming in? And why would there be no inputs? Well, maybe the user hasn't configured their input device, or maybe there is no audio input source. In that case, in would be actually a null pointer. And if in is null, we need to do something. We can't just like decide to reference it. That will actually crash the program. I remember when I was starting my audio programming career, I was actually having crashes. My first ever job, I was experiencing crashes due to this. And I remember somebody by the name Eric Eisenman, wherever he is, he was actually my audio programming mentor. He was the one who actually taught me about doing what we call safety checks. Thank you, Eric, wherever you are. So if in is null, we need to do something. We can't just decide to leave it, and it will crash. So instead, we decide to fill it. So we are filling it. We're filling the output buffer with zeros for now, and then it will decide to start like it will decide to start at out and fill the 256 samples with the value 0. So this normally produces silence, which is what we want. Like, you know, we don't want any input. I hope you understand this concept. I'll repeat again, if you don't understand, you can just write down at the comments, and we'll talk about it. Okay, then we are returning PortAudio continue. This tells PortAudio to continue. So we're going to do, I think what we're going to do, we're just going to write code for now. Then I will just explain everything. So unsigned. No, we've already done these because we've already returned. So we're just going to the main. Yeah. So we're going to do p error. Error. Let it be initialized. Oh, oops. Just going to undo that. To PA underscore initialize. So we're going to initialize it. And then after initializing it, yeah, so we're going to do the if error. Is not equal to what? Just going to do the peer error. So what are we going to do next? Going to open. We are going to decide to put the initialization error, PA get error text. Yeah, but we'll change this to 1. We're not going to do. Yeah. Yeah. So that's we're going to do a PS stream. Okay, PS stream. I think we can do this first, then we can do the string. I'm going to do a null pointer. I think what we're going to do, yeah, okay. Then we do the PRR, and default. I think we'll just use IntelliSense for now, and and do everything for us. Let me just confirm this if I'm okay, if I'm correct. Yeah, I see the problem. Perfect. We're doing the stream pointer. The stream, we have the input. start stream. Yeah, I can see they're a bit. It's almost correct. Just stopping the stream. So we are checking. Yeah. All right. So let me explain what each is actually doing. Why are we getting this? Just check. I'll just try to run that. I'll just check it out. Okay. It's not supposed to bring any errors right now because it's just a simple application. We'll just check it out when we build. And yeah, so what's happening here? So this is actually the main processing loop. I think where had we left? So this is the main processing loop because, you know, if we don't have inputs, we enter this loop. So this is where the actual signal processing is actually happening. And in this case, we are doing the simplest thing, like, you know, just a simple pass-through. So the loop is actually iterating from 0 to 255 since frames per buffer. Yeah, 255 because, you know, the frames per buffer is actually 256. So for each iteration, it's actually copying the, you know, the ith or the I sample from the input buffer to the ith position in the output buffer. So we are actually, like what IntelliSense had actually told us, like it's a simple pass through. So we are just passing the audio straight through, like, you know, the sample at index 0 in the inputs becomes the sample at index 0 in the output, and so on. So normally in DSP application, so this is where we normally do, like, you know, something interesting, like we can decide to multiply the sample by a gain factor. So we can decide to do amplification, attenuation, or we can decide to add it to a filter calculation, or sometimes we can decide to mix it with other signals, or sometimes we can even decide to send it to an effects chain. So, but the structure is actually normally the same. They actually iterate through the samples and do something with each one. Yeah. All right. So it's actually returning a value, and we're actually returning PortAudio continue. So we're actually telling PortAudio, like, you know, I processed the samples successfully and I want to keep processing audio. Call me again with the next, like, samples, the next 256 samples. So maybe you may be there and you're wondering, okay, why do we have a separate callback function? Like, why can't we just process audio in a loop in our main, you know, the main function? So this is my answer, it's actually about real-time performance and responsiveness. When you are processing audio, you have to have a strict time, like a strict time budget. You can say a strict time budget, because you have, for example, maybe 5 milliseconds. That is, 256 samples, and 256 samples plus maybe, not maybe, 256 samples plus 48,000 samples per second. So, like, to process our audio before the next chunk arrives. So this way, PortAudio handles this by running the audio callback on a high priority thread, and in this special thread, it actually gets dedicated CPU time and can't be interrupted by any other tasks while the audio callback function is running. So, like, we can say it's getting that CPU's attention. So meanwhile, the rest of our program can run in the main thread. So this way, if you are doing something slow on the main thread, like for example, if we had a GUI, so it doesn't interfere with the audio processing. So I hope you've understood. So this two-threaded approach is normally fundamental for any real-time audio programming. So it's actually how professional audio applications keep the audio stream, smooth and uninterrupted, even if the user is actually doing other things. And yeah, so we can do so this is actually the main function. So what we are doing here, what's happening here is this is just a main function. We can see it's the main entry point to our program. So here, Pierre, initialize. So the first thing that we do is actually initializing the PortAudio library behind the scenes. So it's actually trying to discover audio devices connected to our computer, loading the appropriate audio devices, and preparing everything for our audio input and output. And it's actually returning it's actually returning an error value. And normally in PortAudio, every function that can actually fail returns an error. So normally if everything is actually correct, it's actually supposed to say, like, we are supposed to return the PNO error. So if something went wrong, it will return a different error code. So that's why I'm doing this. That's why I'm doing this. This is actually error handling. So this is actually, like I said before, this is actually the best practice to check if initialization succeeded. It's actually going to prompt us, like it's going to show us in the terminal. So it checks if initialization is succeeded. If there is an error, like, that means something went wrong. And okay, getting an error there. Okay, so what we're doing here is actually error handling. So this is actually error handling, and it is actually the best practice. We are checking if initialization actually succeeded. If not, you'll get something went wrong. So Okay, yeah, so it's going to see out the PortAudio initialization error, and and the error stream. So this is just basic stuff. I'll just call this basic. This is basic for any C or C++ developer, so you should know the basic part. Yeah. Okay, so we're going to the PortAudio stream, and the stream, so the audio, yeah. So this is normally, it's actually a PortAudio's representation of an audio stream. So what it does, it actually contains all the information about the stream. So which device, the sample rate, the callback function, and all those other stuff. So we are declaring it as a pointer to one, and initializing it to a null pointer. So as you can see from here, default stream, the PA open default stream, this function actually opens a stream to our default audio device. So okay, let's decide to break this down. Let's just break down all these parameters for us to understand everything. So we have this, and this is actually an address of the stream pointer. So we pass the address, so PortAudio can actually fill in the stream object for us. And number one, as you can see, it's the input. So it's the input like we want. So for now, we just want one channel, which is mono. We have mono and we have stereo. So right now we just want mono for inputs, and one for output. That is another mono for the output. We have this, and this is just a sample rate. As you remember, this is 32-bit floating point. So each sample is actually represented as a float from my -1 to I think 1.0. Yeah, I think from -1 to 1.0. Then we have the sample rate, as we had talked about the sample rate at the beginning of the video. We had defined it as 48,000, and we have the frames per buffer we defined also at the beginning, which was 256, if you remember. And also we now have the audio callback. So this callback function, we defined it, and I think I know what's happening. Yeah, it's okay. Because I was checking if I have done I was checking if I had done a typo error, because it's not supposed to be read, because yeah, it's okay, it's fine. Okay, we'll just build and we'll test it out. So the audio callback, so this is actually the function that we actually created initially, if you can remember. And so what will happen here is what do we call this? PortAudio will actually send the audio data to this function. So you have the null pointer, and this just user data to actually pass to the callback. So we are not using it, we just want to pass it as null. And so basically if I can explain it in one sentence. So what you're saying is open a stream with one input channel and one output channel running at 48,000 hertz with 256 sample buffers, and call my audio callback function whenever you have the data to process. Okay, so what you're having here, this is just another error handling technique I'm using. So again, we are actually checking, like, you know, if the default, open the default stream. Yeah, okay, yeah, it's okay. Yeah, we're just checking, like, you know, if open the default stream was successful, and you know, if not, we print an error, but you know, you just print an error. But I want you to check something. I want you to look at this. This is a bit different from this one. Here we are doing what we call terminating. So this is actually cleaning up the PortAudio library, because we already called the initialize. You remember the initialize we had done? So it's always important to do cleanup after yourself. Yeah. Yeah, you get to clean up after doing the business. Yeah, so you get to clean up after what you've, you know, you've initialized and all that. So back here, okay, yeah. So we are starting the stream. So what's happening here is we are actually starting the stream. It's actually starting the audio stream, and as soon as we are calling these, PortAudio starts calling our audio callback function repeatedly with audio data. So if there's an error, it's actually going to close the stream and terminate, like, you know, terminate the PortAudio and give us an error, like, you know, it's going to print out like PortAudio start stream. Yeah. So this is something I want you to understand. This is very, very important. Like, when an error normally happens, you need to clean up whatever succeeded before the error. So if you need a stream, you actually close it. If you initialize PortAudio, you terminate it. Otherwise, you leak the resources. Right. So what's happening here is actually we are actually now running and waiting. Yeah, you know, audio processing has started. So we are actually just printing a message to the user, tell him what to do. So they're going to press in the enter. Then stop stream. So we are actually, you know, stopping the stream, calling like we are stopping actually calling the callback function, and what it will do, it will actually stop the audio flow. Then we have, you know, the close stream. This is actually deallocates the stream object and releases the resources. Then terminates. Sorry. So we have the terminate. This is actually cleanups now the entire PortAudio library, and you know, it's supposed to have something like I think you're going to include something else here. Yeah, I want to so that when we terminate, we have something like our what can I call it? Like, you know, I think I'm going to add something here. The same thing, but I just want us to have exactly so that we can just follow what I had done. And yeah, so we're just going to save this, and we're going to create CMake, like, you know, CMake lists. So we're going to do a CMake text file. Sorry about that. CMake lists. Okay. So I hope CMake is actually what's happening to my yeah. I was wondering where my cursor was. So I'll just write this down, then we'll explain line by line. So I'm going to do a minimum required of version 3.15. I think that's the best. 3.15. And we're going to do project. What do we call it? Audio demo. Yeah, let's call it audio demo. And going to the next, we're going to set standard to, but we're going to change it to 17. And we're going to find the package. Fine, let's go package. What is it called? I think it's called the PKG. Okay, configuration required. It's supposed to be in capital. Yeah, we're going to check, but no, we're not doing the SDR2. We're doing PortAudio required port. Yeah, it's actually, see, it's actually giving us what we're supposed to do. Yeah. How am I doing it again? Joshua, basi utaosha gari asubuhi. Hapana bwana. Hapana. Gari imekuaga safi, gari jaitoka tangu. Hapana. Kitu tutafanya, utamka asubuhi uoshe gari, mimi nitaiacha. Hapana. Kuna bwana. Sasa siwezi kula na bado na record. So let's try and build it. So we're going to create build folder, then we're going to navigate into that folder, then we are going to CMake it and wait for it to run and do everything. Perfect, it found everything. So we are just going to make. It's important for you, if you're using any CMake as the build system, it's important for you to know and understand CMake. So let's make it. Oh, it's already built. That was fast. So we're going to run it. So what did we call it? Audio underscore demo. So what did I do? Where's my cursor? Audio underscore demo, and boom. Yeah, so it's running. So it's saying clean audio running. Press enter to stop. Very nice. So if you're keen, you're able to monitor your audio from your speakers, or for my case, from my headphone. I am able to listen to what I'm talking through the headphone. It's like monitoring. So this is it. This is our first DSP application. So we're just going to recap the concepts. Okay, I'm just going to stop this because it's kind of confusing me. Yeah, and it's actually closed, so there is no feedback. So we're going to recap the key concepts that we covered. So we said we have what we call from my notes here in my notebook, we have what we call the digital signal processing, which is actually converting audio from continuous analog waves into digital numbers, then manipulating these numbers. We talked about sample rates, where we said how many samples per second. So in our case, if you recall, it was 48,000, and based on the Nyquist theorem, we need at least twice the highest frequency we want to represent. We also talked about buffer size. So we said how many samples we process at a time. That was 256. And we said smaller buffers is equals to lower latency, but more CPU demand, or we can say CPU overhead. Larger buffers, we said, is less CPU power, but more latency. And we also talked about callback, the callback, or you can say the callback architecture. We said the audio callback function gets called repeatedly while the stream is actually running. So it's our job to fill the output buffer. We also talked about thread safety, and the callbacks run on high priority audio thread separate from the main thread. Let me just close this terminal so they can get, yeah. So we said it actually runs on high priority and separate from the main thread. Then we talked about error handling, and always check for errors and clean up resources properly. Okay, this is what I can say about our program. So this is the audio flow. We have my voice coming into the microphone. Then we have the analog to digital converter, and then we have the digital samples. So from the digital samples to our callback function, then it undergoes the processing, then the processed samples back to digital to analog converter, to our speakers, then to sound. So this is the foundation of real-time audio processing, audio programming, and in future videos we are going to build on this by adding now actual DSP effects, filters, compressors, reverbs, and more. And you will see that everything follows the same architecture. And if you found this helpful, please like, subscribe, and support the channel. And if you have any question, anything about the code, drop them in the comments below, and I will answer them, or anyone from the audio programming industry will help you with with coverage and answers. So thanks for watching, and I'll see you next time. Goodbye.